welcome to another video on Norton's theorem. In this video, we will find the Norton equivalent of the circuit, and to do that, we need to know the Norton's current and the Norton equivalent resistance when all the independent voltages are turned off, voltages and currents are turned off. And to find I of n, the first thing we want to do is that we want to connect a short circuit across this terminal, and the current flowing through the short circuit would be our Norton's current. And now we can determine the Norton's current using nodal analysis. So we have, say, one node here, and an essential node here, a reference node here. So we label this as node 1, and we'll label this as node 2. So we know that because of this short circuit, V2 is equals to 0, and that would mean that the voltage drop V2 is equals to V0, which is equals to V0. That means that this is 3 V0, this V1 is 3 V0, and that would mean that V1 is also equals to 0 volts. Okay. Then the next thing we want to do is to calculate IN. So if you come here to write the node equation here, we will say that 20I plus, this is 0, that will be V0 over 25, which is 0, then plus IN equals 0. And this would mean that IN is equals to minus 20I. And I is the current flowing through this 2 kilo ohm resistor. Sorry about this mistake. To calculate the value of I would be V1 minus 5 divided by 2000 ohms. Then there will be a minus in front of it because we want it to go in this direction, not outside. So that would be minus 0 minus 5 over 2000, and that would be equals to 2.5 times 10 raised to the power 3, because it is not flowing out of the node, it is flowing into the node. So we know that I is equals to 2.5 times 10 raised to the power 3. So for that reason, we know that I of n is equals to minus 20 times 2.5 times 10 raised to the power minus 3, which would be equals to minus 0.05 amperes. In other words, the current is flowing upward. Then the next thing we want to do is to calculate R of n, and to do that, we just put up this independent power source and plug in a test voltage at the terminals. And the test voltage of 1 volt that we're going to plug in, the current that we get from it, the inverse of it will be the resistance R of n. The circuit will look like this, the circuit that I want to use to calculate R of n. Then what we'll do next is we'll connect our voltage source, our test voltage source here. So what we can use mesh analysis to find the value of the current I flowing out of this place. So we know that the current here is 20I, and we know so let's say this is I1, this is 20I, and the current here is I2. Since I is the current flowing through this 2 kilo ohm resistor, we know that I2 is equals to minus I. We also know that V naught is 1 volt since it is connected across the resistor, so this will be 3 volts. So V naught is 1 volt, and then this will be 3 volts. That would mean that the current I would be minus 3 over 2000, and this minus is there because of the direction of the current flow. So we would have 3 divided by 2000, which would be equals to 1.5 times 10 raised to the power minus 3 minus 3. I want you to realize that I1, which is the current flowing in this direction, is the sum of the current flowing here and the current flowing here. So that means let's call the current here I0, and that would be 1 over 25. So we know that 20I plus I0 equals I1. That would be minus 1.5 times 10 raised to the power minus 3 plus 0.04, I guess, should equal 0.0385. That is I1 is equals to that, and that would mean that R of n is the inverse of it, which would be I just now realized my mistake, that this should be minus 0.03. I forgot to multiply by 20, and this should then amount to 0.01, and the inverse of that would be 100 ohms. So the Norton equivalent circuit would look like since the current flows downward, look like this, and we would have 0.05 minus 0.05 and 100 ohms. Thank you for watching. Don't forget to hit the like button and subscribe. See you next.